And I'm a sophomore in the Rendell Research Scholars Program studying aerospace engineering. This semester, I worked with Dr. James Hubner in the Aerospace Engineering Department in the development of a luminescent pressure and strain measurement technique for aerodynamic testing. Before we move into our actual measurement technique, it's important to understand why this data is important. Pressure data provides a relation to the forces that an aerodynamic specimen may experience while in flight. This can be things such as lift, drag, or thrust, or any other aerodynamic or atmospheric forces experienced. Strain, on the other hand, allows us to analyze the structural data of that specimen, understanding if it is under tensile or compressive forces, if it will experience a bending force, and how that may warp, damage, or destroy that object. There are two common measurement techniques currently utilized in the aerospace field. For pressure, it is most commonly used that pressure taps measure the strain, or the pressure, excuse me. These are small holes drilled in the specimen that are then connected via flexible tubing to pressure scanners that actually measure the pressure. For strain gauges are typically used. These convert the strain experienced by an aerodynamic specimen to be converted into electrical signals that are then read by a computer. Both of these methods are extremely accurate at providing local data, however are expensive and time-consuming to install, which can prove to be problematic in the long run. In place of pressure taps, pressure-sensitive paints, or PSPs, are proposed as an alternative. PSPs utilize a unique oxygen-sensitive fluorescent molecule to provide visual data for pressure. Upon excitation by a light-emitting diode, or LED, the molecules within the PSP are excited. Upon recovering from this excited state, they emit a photon. This photon and the intensity of the photons emitted from the PSP are then measured and can be related to pressure. However, as mentioned previously, PSPs utilize this unique oxygen-sensitive fluorescent molecule. So in the presence of oxygen, or O2, this process is non-radiative, meaning a photon is not emitted. Since oxygen is a constant fraction of air and therefore air pressure, this can then be related to the pressure in the atmosphere depending on the oxygen and the intensity of light. So this intensity is inversely related to the pressure. Upon capture of images in the intensity of light emitted by the PSP, a false color map, as seen in the image on the screen, is placed over the specimen that allows us to visualize the data by the naked eye. As seen in this image, high pressures are denoted by reds and low pressures are denoted by blues. In place of strain gauges, photoelastic coatings, or PECs, are proposed as an alternative. Similar to PSPs, PECs also utilize the intensity of light. However, the intensity of light at specific polarizations of that light, meaning the angle that it's returning to the eye or to the camera, is what is important in determining the strain. Within a strain on a specimen, this bends or warps the specimen in such a way that the rigid photoelastic coating that is placed on top of it is also warped. This allows for the polarization of the light to change and be registered by our camera. The intensity of this light is analyzed at 4 different analyzer angles. The 4 specific analyzer angles that are utilized are 0 degrees, 45 degrees, 90 degrees, and 135 degrees. The intensities at these angles are then fit to a sine curve as seen on the screen, which allows us to determine not only the strain on the specimen, but also the principal direction of that strain on the specimen. So on this slide, you see 2 images that denote our lab setup. So starting with the lamp, or high-intensity LED. This LED is currently now 2 LEDs. We're using both blue light and red light, which allows us to interact with both the PSP and photoelastic coating. Followed by that, we have a linear polarizer and quarter wave plate. In order for our light to be effectively registered and interact with the PEC, it must be circularly polarized, so that once it returns, it will have a linear component, making it elliptical light, and therefore understanding the strain on the specimen. The light then reaches our chamber where our specimen is actually held. This semester, we used an aluminum cantilever beam that had the photoelastic coating with the pressure-sensitive paint oversprayed on top of it. The light is then emitted and reflected through this chamber and interacts with our camera, high-pass filter, and emission filter. This camera includes a micropolarization that allows us to polarize each pixel to create those polarizations as mentioned previously with the strain. Also within that chamber, we are able to set dynamic and static loads and set specific pressures to be used for our references. So now moving on to data collection. As we move forward with our data collection, we first set up our specimen and set the load that we are willing to put on it, whether that be a static or dynamic load, with dynamic loads being an oscillating load. We then set our pressure and turn off all the lights in our lab. We then take a dark image, which we can later use to equalize our image, as I will talk about in a second. Once that is all complete, we turn our lamp on and we begin capturing images. Once the image is captured, as seen on the left, we have to crop down and isolate a region of interest as seen by the arrow and the second image. This region of interest is simply where our PEC and pressure-sensitive paint lie on our specimen. After this has been done, we equalize it using that dark image and a factory flat field, which is provided by National Instruments, the provider of our camera, to eliminate any light pollution or distortion that may be seen from the camera, anything like that. Once this region of interest has been equalized, we utilize the polarization of the pixels as seen by the camera. The camera polarizes each pixel to one of those analyzer angles, 0 degrees, 45 degrees, 90 degrees, and 135 degrees. Then we then cluster 4 of these pixels together to form what we call a superpixel, and this is what we use as our point of analysis. We take the average intensity of these 4 pixels within a superpixel to relate to the pressure on the surface, whereas the standard deviation of those 4 pixels within the superpixel can be used to create the sine wave, which we then use to determine the strain on the specimen. So here we have some results taken prior to my involvement with the project. On the left, you see pressure data. So this pressure data, the axes on here relate to the number of superpixels on the specimen. And as you can see, a high pressure is denoted by reds. And as you progress to orange, green, and blue, the pressure decreases. On the right is strain data. So on the strain data, you can again see a low strain is denoted by blue, and as colors progress towards the red spectrum, there is an increased strain. Strain is simply the amount of warp or distortion on the object as it is undergoing its load. Moving forward into the future, next semester we will be moving into Hardway Hall to the supersonic wind tunnel here at the University of Alabama, where we'll be using a new specimen as seen on the top, which will allow us to have dynamic loads that will oscillate in the wind tunnel and be able to understand in non-controlled settings. Furthermore, we will be transferring our data analysis away from LabVIEW into MATLAB, where we can more effectively analyze the images. At this time, I would like to open the floor to any questions.
On slide 8, you mentioned how the paint is over the coating. How is it that the paint does not interfere with the coating's results?
Yes, thank you for that question. So when we move into our analysis and create our specimen, we put our photoelastic coating on the specimen. And after that, it is sent to a company called ISSI, which is a leader in PSP technology. They spray a very thin layer of the PSP, making it optically thin or not optically thick, meaning that it is slightly transparent and the light can pass through it, allowing it to interact with the PEC.
On slide 10, you talk about the analysis of the superpixels. How does clumping the 4 pixels together affect results?
Yeah, so the camera that we are utilizing is extremely high quality. Our photos are taken with 1820 by 1200 pixels, which is extremely high resolution. This allows us to spatially take 4 of those pixels and convert them into a superpixel and effectively use that as a point and be more effective in providing full spatial data as compared to pressure taps or strain gauges. This, in essence, provides a full spatial map as seen in some of the previous images, which we can utilize over and integrate over the entire specimen.
Why do you think that these methods haven't become more mainstream yet?
So these methods are actually being used quite frequently throughout the field, especially pressure-sensitive paints. This is a very specialized technique that's specifically used for wind tunnel testing. In order to have this entire setup be accurate, all of the lights must be turned off, so it must be in a room, so it cannot be used in traditional lab setups where there's a lot of light pollution, a lot of computers, things like that. Wind tunnels, on the other hand, are typically in dark spaces and can be controlled in settings. And while you may not see photoelastic coatings or pressure-sensitive paints in your common hardware store, you can see them still with typical distortion of light, whether that be a plastic that you bend and you notice a rainbow being formed in it, something of that nature where you're noticing the light is changing.